And then lastly, the stub area flag needs to be the same. The stub area flag denotes whether this is a stub area or a normal area. We'll talk more about stub areas once again in later slides. Now let's talk about designated routers and backup designated routers. In this topology I have 6 routers connected to the same Ethernet segment. So assume that these 6 routers are connected to a switch or a hub, all sharing the same Ethernet segment. Designated routers or DRs are used on broadcast multi-access environments such as Ethernet and certain WAN implementations such as non-broadcast multi-access environments in frame relay. So to explain why we have a designated router, let's assume that this network 10110 is connected to router 1 and the 6 routers are connected to this Ethernet segment, and assume that this network goes down. So let's assume for the moment that there's no designated router on this Ethernet segment, and hopefully you'll quickly see why there's a requirement for a designated router. Without a designated router, all of these routers would have a full adjacency. In a full adjacency, LSAs are exchanged between routers. So in this example, R1 needs to notify the other routers using a link state update that there's been a change in the network topology. So R1 will send an update to R3, send an update to R2, to R4, to R5, to R6, notifying all of the routers that there's been a change in the topology. R2, when receiving that update from R1, in this case, because there's no designated router, has a full relationship with all other routers, so it sends an update to all of its neighbors to notify them that there's a problem. The same will happen on R3. R3 received an update from R1, so it notifies all of its neighbors that there's been a change in the topology. R4 will do the same thing. It receives an update from R1, so it sends an update to all of its neighbors. And I'm sure you're getting the picture now. R5 received that update from R1, so it sends an update to all of its neighbors. And lastly, R6 sends an update to all of its neighbors. So there's a lot of duplicate traffic when a single network goes down, and these 6 routers have a full adjacency with one another. So rather than doing that, a designated router is selected on this specific segment. So let's assume that R2 was elected as a designated router. Designated routers are selected on 2 criteria. The first one is highest priority. You can specify the priority on an interface. The default priority is 1. 0 excludes a router from becoming a designated router or backup designated router. The values for the priority are from 1 to 255. So the first criteria is highest priority. If the priorities are the same, then the router with the highest router ID is elected as the designated router for that segment. So in this example, we've elected R2 as the designated router, and let's assume again that this network goes down. But what happens now is R1 sends an update only to the designated routers. Designated routers are listening on this multicast address 224.0.0.6. Other routers are not listening to that multicast address, so from an ospf point of view, they do not receive or see that update. Only the designated router receives that multicast update. Now, multicasting isn't covered in this course, but briefly, if this infrastructure was a hub, so the routers were connected via a hub, at layer 1 that multicast would go to all the routers. However, only certain routers are listening or accepting that multicast. So only certain routers have subscribed to that multicast. In this case, only designated routers are listening for and accepting multicasts to address 224.0.0.6. So the other routers at layer 2 will drop this update. ospf residing at layer 4 in the OSI model will not see this update on the other routers. So routers 3, 4, 5 and 6 from an ospf point of view at layer 4 will not receive the update. Only router 2 will receive the update. So logically what happens? The link goes down. Router 1 is updating router 2, the designated router, by sending a multicast to this address. Only router 2, the designated router, is receiving the multicast. Router 2 then sends an update to all the other routers on this multicast address, 224.0.0.5. all ospf routers are listening to this multicast address, so they will receive the update. Router 1 would receive the update but wouldn't process it because its ospf topology table is already up to date. So logically what happens is the update goes from R1 to R2, R2 sends that update to all the other routers, they process the update, and therefore their topology database is updated with the new information that this network has gone down. As you can see here, it's much more efficient to use a designated router than to allow full adjacencies between all routers and have all those duplicate updates. It's important to realize that only the designated router and backup designated router will have full relationships to all the other routers. So for instance, router 4 and router 5 will only have a state known as two-way. In two-way, they know about each other, but no updates will be exchanged between the routers. So in other words, R4 and R5 will not update each other, neither will R5 and R6, and so forth and so on. All routers will only update the designated router and backup designated router with changes in the topology. So they have a full relationship to the designated router. This allows for the saving of updates and duplicate traffic on a single segment. Once again, it's important to realize that routers on this segment will only form full relationships with designated routers and backup designated routers. Now in this example, I've only got a designated router. The issue with only having a designated router is that if this router goes down, updates will not be sent and received properly. So on a segment, a designated router will be elected, and normally a backup designated router would also be elected. So you'd have both a designated router and backup designated router. The BDR will become the DR if the DR fails.